Let's talk a little more slowly than we did in class about how we delete nodes from a binary search tree. So here I have a binary search tree with integer information in the nodes that I've labeled here. So let's think about how we would delete various nodes from this tree. So let's say we want to delete 60. Well, first we would find the node if we were looking for the information, right? So we start at the root, which is 100. 60 is less than 100, so we go left. This node is 10. 60 is greater than 10, so we go to the right. This is 20. 60 is greater than 20, so we go to the right. This is 80. 60 is less than 80, so we go to the left. 60 is less than 70, so we go to the left again, and 60 and 60 are equal, so we found it. Now we look and see this node, 60, if we think about how we code it, both of its children here are null, right? It doesn't really have any children. Which means that there's nothing else that we have to worry about sort of moving around. We can really just erase 60 from this tree. And we would need to make sure that 70's left child is now null, where it wasn't before, right? It was 60, now it's null. So that's how we delete a node with no children. We just reset basically the correct child of its parent, right? Singular parent. 60's parent was 70. We reset the left child of 70 to be null. Okay. So now let's think about how we delete something with one child. And for that, we'll go to 10. And 10 only has one child. It's 20. And we know that everything, sort of this portion of our tree, everything that we got to by going left from 100 is less than 100. So when we delete 10, we can just sort of reconnect 100 to that child of 10, which was 20. And all the children of 20 are still moving in the correct directions. They have the right relationship to 20. So when we delete a node with one child, its child becomes a child of its parent. Right? 100 was the parent of 10, which is now gone. 20 was the child of 10, and so now 20 is a child of 100. So those cases aren't too bad. The tricky case is the one where we delete a node with two children. So I'm going to erase this and redraw part of the tree to give us a few different situations to look at. Okay. So 10. Sorry, let's draw this as a node. 10, 20, 20, 80, 70, and I'm going to give 10 some more children. So let's have 1 over here, and then 2, and then 5, and then 3. Okay. So now let's say we want to delete something with 2 children. So let's start by looking at 200. 200 has 2 children, 150 and 300. And so we can't just sort of remove 200 from the equation and connect 100 to 150 and 300, because then 100 would have 3 children, and it's only allowed 2. So we really need something to replace that 200. So we're going to look for a successor. And we'll use the greatest value that's less than what we're deleting. Right? And less than what we're deleting means we want to look left. But the greatest value means we want to go as far right as possible. So in general, the path we'll take from the node we're deleting is 1 step left and then as far right as possible. And the node sort of at the end of the line will be the successor. So here we do that 1 step left, and then we can't go any further to the right. So our successor is 150. Right, and if we look at the values in the tree, that makes sense. 150 is the greatest value less than 200. And so we're going to sort of move that 150 node to the 200 spot. We delete the 200 node, and we're going to move this one up. So now this node is 150. And 300 stays as a right child, because 150 was less than 200, so 300 is definitely greater than it. So that wasn't too bad a case. We didn't have to juggle too many things. But what if we tried to delete 10 instead? So now we're deleting 10. Let's look for a successor. So we're going to go 1 step left, so that we're looking at something less than what we're deleting, and then as far right as possible. So we go left, and then as far right as possible, and that gets us to 5. So 5 is our successor. So somehow we want to move 5 up here. So let's go ahead and do that. I'll replace this 10 with a 5 and get rid of the 5 down here. So now that 5 is the successor to 10, so we replaced the 10 with it. But now we have to do something with this 3 that was a child of 5. It can't be a child of 5 anymore, because we put 5 in the spot where 10 was, so it has children 1 and 20, right? 10 had 2 children. That was what made this hard. But we can make 3 one of the children of 2, right? 2 was the parent of our successor. So the children of the successor become children of its former parent. So 5 was a right child of 2, so 3 should become a right child of 2 as well. And we know we won't end up with too many children here because we sort of went right as far as we could. So there can only have been left children of the successor, no right children. And we just moved one of the children of 2, right? We removed 5. So we're sort of slotting the left children of 5 into that right child spot of 2. So one of the things posted in the binary search tree content page is an animation where you can insert numbers yourself and build trees and delete things from it. So I really recommend playing around with it to see more of how this process works as you work on writing the code.